All right, well, let's next look at heap implementation details. Conceptually, it's best to think of a heap as a binary tree, meaning you have a node, and it can have at most 2 child nodes. It's actually going to be implemented as an array. So we're going to have an array, and you know that first node is going to go here, the first child of it there, the second child of it there. So why would we want to implement this as an array instead of the sort of more natural way to implement a tree, which is using pointers? Well, this is something we'll get into the details of pretty soon. But for now, it's enough to just realize that when you do this as an array, there's no pointer following, there's fewer heap applications, and no pointer storage. So why do we want to do this as an array? It's faster, has better data locality, which is a focus of another lecture, and uses less memory. So those are 2 very good reasons to do something, faster and less memory. You don't usually get those together, but you do with an array. All right, well, if I have a binary tree, what's the relationship among nodes in the tree? Well, we have the heap property, which says for any given node, its key value is less than or equal to its left child and less than or equal to its right child. So what does that mean for the minimum key? Where can you find the minimum key in a heap? Well, the minimum key has to be at the root. And then the key values just get larger as you go down the tree. So for example, here's a heap where I've stored the vertices in a graph, and maybe the key value refers to like the shortest path to that vertex. So the vertex V has a current shortest path of 12. And likewise, vertex Y has a current shortest path computed to it as 18. So the minimum key will always be at the root, and the reason for that is, every node has this property where the 2 keys below it are greater than it. But that doesn't mean that a heap is unique. So if you have a set of data, you could have a heap that looks like this. The minimum value is at the root, but this could also appear in a different configuration. So for example, we've got a 4 here, a 4 here, a 4 here, and over here the 4's here, 4 here, and 4 here. If you notice, this 4 here is lower down in the tree compared to this 8. And that's completely okay because they don't have a parent-child relationship. The 4 is greater than or equal, and the 4 is greater than or equal, which means we're satisfying the heap property, and we don't have to worry about this relationship. That would be considered the the uncle or aunt node. We don't have to worry about that for this problem. Okay, well, if we have a heap, and I told you it was stored in memory, this is what that looks like. This is sort of conceptually how you should think about it, but this is how it's actually laid out in memory. So this first 4 shows up here. Its 2 children are right next to it, and then the 9 shows up here, the 4 here, the 12, and so on. So if you want to know how a heap is stored in memory, you just start at the top, and then snake your way through the tree, and that's the order. So this thing will be at index 0, 1, 2, 3, 4, 5, 6, 7, 8. All right, well, why is this useful? One of the reasons that we might want to store something in a tree is because we want to traverse the tree, meaning we go down to this node and then we come back up to the parent. Well, we can still do that in an array. So let's just start by computing the index of any given node's parent. So for example, for this value here of 4, it doesn't have a parent, so we can just put there's nothing there. For this node 4, the index of its parent is this thing, which is at index 0, and the 8th thing is also at index 0. So take a few minutes and sort of fill out the rest of this, at least in your head. All right, if you take the time to do that, the first node doesn't have a parent. The next 2 nodes have a parent of 0. The next 2 nodes have a parent of 1. So, these 2 nodes, its parent is this 4, which is at index 1. The next 2 have a parent of 2, 3, and then the next 2 will be 4, and then the next 2 after that will be 5, and continuing on. So a more interesting question is, what's an equation for going from a current node's index, so for example, the 3 here, to the parent index. So if I want to traverse this tree from this 9, and I want to get to the root, I need to go to the parent, and then I need to go to the parent's parent. So how do I compute those indices? Well, to compute the index of a node's parent, you take the current index, subtract 1 from it, and then divide by 2. This double slash just means I want it to be integer division. And that's opposed to just like floating point division where we'd end up with a fractional number. So let's do this for an example to make sure it works. Let's say we have this, this value 5. We want to compute 2 to be the index of the parent. So we would take 5 minus 1 divided by 2, and that would be 4 over 2, which is 2. So it at least checks out for that example. And if you were to run that through any of them, you would see that that's going to always compute the correct index for the parent. All right, well, the next question then is, how about the index of a node's 2 children? So this root has a child to the left and a child to the right. The index of this child is 1 in the array. The index of this child is 2. So the left child index is 1. The right child index is 2. How do you calculate the indices of a node's children in the more general case? And that'll take 2 equations. Well, moving on, we have this node here, which is at index 1, and its children are at 3 and 4. So I'll fill that in, 3 and 4, 5 and 6, 7, 8, and I've graded these out just to denote, those don't actually show up in the array or the tree, but we can always compute the actual indices for them just so I can show you how it's done. So what are the equations for computing these? The left child index is always going to be 2 times the index of the current node plus 1, and the right index is just 2 times, well, it's just this plus another 1, and that's going to give you this other equation here. So why do we go through this trouble of figuring out these equations? I just want to make it clear that it's constant time to go from a from a parent to its child. It's also constant time to go from a child up to the parent. And we can do that just using the simple arithmetic. All right, so between this video and the next video, you should work on the exercise for this set of lecture slides.